Welcome to a crash course on acids and bases. First up, we have the Bronsted-Lowry acid. The Bronsted-Lowry acid is a species that donates a proton in a chemical reaction, and an example of one is ammonium, which is N with 4 protons attached to it. Next, it also has a positive charge. Next up, we have the Bronsted-Lowry base, which is a species that accepts a proton in a chemical reaction. An example of that is an hydroxide ion. O and a proton with 1, 2, 3 lone pairs and a negative charge. Next we have a Lewis acid, which is a species that accepts an electron pair to form a new bond. An example of that is boron trifluoride, which is boron attached to 3 fluoride atoms. It also has no charge on it. Next we have a Lewis base, which is a species that donates an electron pair to a Lewis acid in order to form a new bond. An example of that is NH3, which is nitrogen attached to 3 protons and holds 1 lone pair that can be donated. So an example of a Lewis acid-base reaction would be the fluoride ion with boron trifluoride to form boron tetrafluoride. Now this specific reaction going this way is a Lewis acid-base association reaction because these two molecules associate with each other. And they do that by an electron push from the fluoride to form this. And this has a negative charge. Now also this can go the opposite way in a Lewis acid-base dissociation reaction where the fluoride ion takes its electron and then becomes dissociated away from the boron tetrafluoride to form boron trifluoride. The acidity of different hydrogens is determined on the structure. And this difference in acidity can be summarized through 4 different effects. The first effect is the element effect, in which the acidity of acids increase toward the higher atomic numbers within a row of the periodic table, as seen here. The main source of this increase is the increasing electron attracting ability when moving to the right of the periodic table. Also, the acidities of acids increase towards higher atomic numbers within a group of the periodic table. The main source of this increase is the decreasing strength when moving down the periodic table, as witnessed here also. The charge effect is determined by the charge of the atom to which the acidic hydrogen is bonded to. So here we have H3O plus, and the pKa is negative 1.7, and we have H2O, which does not have a positive charge, and has a pKa of 15.7. Thirdly, we have the polar effect, in which the closer the electronegative group is to the acidic hydrogen, the more acidic it is. So here we have our acidic hydrogen with no electronegative group, and here we have the electronegative group and the acidic hydrogen, and then the electronegative group closer to the acidic hydrogen here. And this is due to the stabilizing effect of the electronegative group on the conjugate base when the acidic hydrogen is gone. As you can see here, the pKa decreases as the electronegative group gets closer to the acidic hydrogen. Finally, we have the resonance effect, in which as you have more resonance structures, the pKa decreases, therefore the acidity increases. So this group here has no resonance effect, whereas this group here does have resonance effect, and there's a clear difference in the pKa's. Also here, this group does not have a resonance effect, this group does have a resonance effect, and therefore there's a stark difference in the acidities of the two molecules. In all of these effects, the stability of the conjugate base directly impacts the strength of the acid, in that the more stable the conjugate base is, the stronger the acid will be. As you can see in the element effect, the charge effect, the polar effect, and the resonance effect. If you would like to see this yourself, especially with the resonance effect, you should practice it and see what the conjugate base is. This has been a review of acids and bases with Shreyas and Charlotte. I hope this review has been great for you and you've learned a lot. Good luck on the final!